So let us first look at what is called as DC GAN, or deep convolutional GAN as it is called. It's also interesting to note that in any of our treatment, we have not restricted our data to be of a particular modality, right? So we didn't say that the data has to be the image, or it is a speech or anything. All the theory on the treatment that we took so far for variational divergence minimizers or GANs as samplers are data modality agnostic. You can use these ideas with any of the data modality. Okay, so in DC GAN, what people do is, see, typically in a GAN, the dimensionality of Z, which is the input to the generator network, will be some k dimensions, and of course our data, as we said, is some d dimensions. So typically what happens is k would be much lesser than d. The dimensionality of the input random variable is much less than the data dimensionality. So the typical architecture of the generator network would look like this. So you start with some k dimensional data, and then you keep increasing the dimensionality till it goes to d dimensions. So here you have d dimensions. So typically this would be some 16 dimensional data. So Z is in some 16 dimensional data, then you go to some 32, some 64, and keep going, and finally it goes to some d dimensional data, right? This is keep increasing the dimensionality of the generator network. That is how the typical architecture would be, and this can be a multi-layer perceptron or an MLP. Can be a multi-layer perceptron or a fully connected neural network. It is called MLP. In a deep convolutional GAN, right, DC GAN, what is done is, in a DC GAN, convolutional layers is typically the up convolution or transpose convolutional layers. Up convolutional or transpose convolutional layers are used in the generator. Transpose convolutional layers are used in the generators. So what is done? You start with some Z that is in, let's say, some 16 dimensional space, and then you keep increasing the dimensionality of the data, using transpose convolutions, transpose or up convolutions, till a point where it reaches so it reaches the shape of the data. So DC GAN is typically used for the case where the data are images. So data is images of the dimensionality. Images are represented as some row times column times 3, right, of 1 for each channel, red, blue and green. So using transpose convolutions, the final layer would have this sort of a dimensionality, which is comparable to that of the, it's exactly equal to that of the data. So this is row, this is number of channels, number of columns, and you have 3 dimensions here. So the final layer is going to be an image as an output. Typically what happens here in an MLP is that even if you use images, the data is reshaped. So once you get in RD, you reshape in the form of images. Even if you have an image, so what you get is the flattened version of the image, and one needs to reshape after getting the output. In deep convolutional GAN or DC GAN, there's no reshaping operation that is done, but the transpose or upconvolution layers are used, so that you start from a 16 or a 32 dimensional real number space, and then the final layer would have the data in the appropriate shape as that of the actual data itself. You don't have to reshape the data. So that is what is typically referred to as the convolutional GAN. This is specific to images being used as data. Okay. The next architecture or the next improvisation that I want to talk about is what is called as conditional GANs. So also referred to as C-GANs. So far, the sampling that we saw was unconditional sampling, in the sense that once the generators are trained, okay, there is no way that you can control what sort of images that are generated, okay. But in the practical use cases, one would want to generate images that corresponds to a particular class, or let's say a particular textual description and so on, right. For instance, let's say that we are building a generative model on the data set that comprises different types of pictures of different types of animals. Now once we build the sampler, we would want to have a control over what sort of class or what sort of animal is being generated from the sampler, okay. In the formulation that we have seen so far, there is no control so as to how to regulate what the generative sampler is sampling, okay. So now to ensure that it happens, we need to look at what is called as conditional GAN. The data for that particular use case has to be this way, that you have the pairs of x comma y, okay, x1 y1 x2 y2. Note that the data that one would need to build conditional samplers are very much similar to the data that one would need to build discriminative machine learning, which is the classifier. So now this is drawn IID from a joint distribution pxy, okay. So examples can be that your x can be images and y can be a class label or a textual description and so on, okay. This can be a class label, or this can be a textual embedding and so on. Okay, if you don't know what a textual embedding is, don't worry, we will look into this later in the course. Think of it like this is a class label corresponding to x, right. For every x we need a class label, a textual embedding again corresponding to x. So now a textual embedding is that, so let's say that you have some image and a textual description of it. Converting the textual description into a particular vector is what is called as textual embedding. We will see later in the course how to get embeddings of this sort. So assume that we have access to this. So for the ease of understanding, let's say that all we have right now are class labels. So basically we have a data set of images, and each of the image has a particular class label associated with it. You can take the example that I just gave, that we have images of animals, and each of the image has a particular class label associated with it that would signify what particular animal class it is, okay. Now what is the objective here? The objective is to sample from the conditional distribution. Objective is to sample from the conditional distribution. Sample from the conditional distribution Px given y, okay. Now instead of px, so now in the unconditional case we were sampling from the marginal distribution px, right, which had no conditioning variable. Here we need to sample from px given y instead of px. Okay, how do we do that is the case. Thankfully nothing changes in the formulation that we just had. Okay, so what we have to do is that solution is to simply, we need to estimate, we were estimating px so far, right? We need to now estimate px given y, okay, px given y, and make p theta to be close to px given y for all y. Make p theta approach, or like p theta approach px given y, okay, for all y. This is how you do this. Now how do we do this algorithmically is, it's pretty simple. What we need to do is modify the generator and the discriminator, modify the generator and the discriminator to operate on the conditional distributions, to operate on the samples of the conditional distribution, operate on the samples of the conditional distribution, conditional distribution. Now how do we do this? Conditional distributions. Now it's pretty simple to do this algorithmically. What we have is that we have the generator, g theta of z. Now this was already taking samples from normal 0 1 as input, right? Now additionally one should also feed y that corresponds to that particular x as the input. So the class label also goes as an input to the generator. So what does this generate? This generates a sample x cap conditioned on that particular text. Let's call this p theta, okay, of p theta of x conditioned on y. Okay, this is the distribution that we want to model. Now how does the discriminator or the t function look like in this case? Same thing, the discriminator also now will take, so one we had samples of x or x cap, right? I mean this is the usual discriminator. Along with that we will also give y as an input to the discriminator as well. That's all. So now this will be dw of x given y. So this will again give 0 or 1. Okay. Now how does the loss function get modified? So we have j theta comma w is, now we have the expectation of log of this dw network also will take x and y as an input, and the data is now, so x comma y are now being sampled from pxy, okay, for that particular class, plus the expectation of log of 1 minus dw of x cap comma y, and now x cap comma y are coming from p theta x cap comma y. That's it. So nothing changes. Okay, all that we need to do is give y as an additional input to both the generator and the discriminator, and whenever we are giving the samples, we'll have to ensure that we are giving samples from that particular class. So now in the example that I gave, where we have data set of animals with different classes, what we do is whenever we give as an input, let's say dogs images, we'll give one particular label as an input to the generator, and we give that exact same label as the input to the discriminator as well, while we are training the discriminator. That's all. And we can whenever we are giving a particular image as an input, you also append that the corresponding class label as an input to both generator and discriminator. Now, how do we do this? Suppose this is a discrete number of classes that we have. We can use the one hot encoding of these class vectors. So where suppose you have k classes, then each of the classes is represented using zeros and ones, where the 1 will be at the kth location and 0 otherwise. Now that's the usual one hot encoding. I'm assuming that students here know what one hot encoding is. You can just convert each of the class scalar as a one hot encoding and give it as an input to the generator and also the discriminator. This is how one would change or turn an unconditional GAN into a conditional GAN, where we have the GAN now sampling from the conditional distribution. Okay. Now, one other thing that we should see is how do we sample, right, or do inference in a GAN? We have not seen this. It's pretty trivial, but let's do this. So, inference with GANs. What is inference? Inference is nothing but data generation here. Okay, inference with GANs or VDM. So how do we do this? So input, what are we given? We are simply given a trained generator network. A trained generator network. So let me call that as G theta star. Okay, this is what we are given. Now, the output or the objective is a new data point or sample of, okay, so let's call this a sample from Px. A sample from Px, which is not there, which is not present, in D, right? So because we know how to sample from the distribution now, that whenever we do an inference with a GAN, okay, we get a sample from Px that is hopefully not in D. So how do we do this? We just have, we take the trained generator after solving the min-max optimization problem. So we have G theta star, this will take Z as an input, okay. So you take a Z, which is a sample, okay, let's call this as Z test, okay. Now where Z test is some sample that is coming from normal 0, 1, okay. And finally you got an output here, which is X test, okay. Hopefully is a sample from Px, because now P theta has become close to Px if the training has happened properly. This is how you do inference on a GAN. So inference is data generation from a GAN. So now if it were a conditional GAN that you have trained, you should also have Y as an input here, an additional input, and this would be X test corresponding to the given class if it's a conditional GAN, corresponding to the class or class label specified by Y. Okay, this is how one uses a GAN for inference. So let me just show you an example of how a GAN is used for inference. Now there is this website called this person does not exist. Okay, so what is actually happening is that every time, okay, so maybe this is the resolution is not compatible. Okay, so now this is a picture of a person who does not exist. Okay, really. So now whenever I refresh this web page, so what is happening is a Gaussian random variable is being generated and it is being passed through a trained generator network, a trained GAN network, and it is giving you an unconditional generation. Okay, so these are the pictures of people who does not exist in the world, but what it is doing is that you have trained the GAN. Okay, this is actually a style GAN. Okay, there is an architecture called style GAN by NVIDIA. So now this is the inference that is being done on the style GAN architecture. So every time I'm refreshing, what is happening is that a sample from the Gaussian distribution is being generated, and it is being passed through the pre-trained generator, the generator network, and you are getting the image that is being generated at the output. Okay, this is the unconditional generation because there is no control on what sort of pictures that I am generating. So one can also make it a conditional generator where suppose you have data of human faces where each of the face had a class label. Let's say it's a boy or a girl or an adult or a female or anything, right? So one can give that as an additional input to your generator while generating, and you can control whatever image that is being generated. Okay, so now that is how one would use a GAN for the inference.